Hi everyone, and welcome to this video on solving polynomials and the zero product property. That's the goal of today, is figuring out how to solve and using the zero product property. So if you thought, oh my goodness, I'm so glad that factoring is done and over with, think again, friend. It is always going to come back to haunt you. So let's get into it. First things first, we need to define what the heck a zero is. We've been talking about it inadvertently every single day in class, but we really gotta figure out what the heck is a zero. And no, I'm not talking about the dog in The Nightmare Before Christmas. A zero is just another name for an x-intercept. So when we're graphing, we have our y-axis. Horizontally, we have our x-axis, and a zero is just wherever it crosses the x-axis, right? It could be right here at -1, 0, or it could be over here at +3, 0. And maybe I have an odd polynomial that has a multiplicity of 2, and it goes like this. Pretend that's going through 3, but we could have an odd polynomial, an odd negative polynomial that looks like this, right? But a zero is just an x-intercept, and we know that x-intercepts have to go through the x-axis. If it didn't go through the x-axis, then it would just be another point. Like if it went through 3, 1, and maybe that's floating up around right over here, we know that that's just a regular point because all x-intercepts are of the form a number x, 0, or more specifically, the y value is 0. That's super important detail. And that's actually why we got the name zeros for x-intercepts, because the y values are 0. And something that's a little bit more conceptual is a lot of times the y-axis, this like up and down y-axis, tells us like a height, like as if you were drawing a little person, right? So that tells us the height. And so a lot of times when we have an x-intercept, the height, oops, sorry, the height is 0 as well. So like right here, that has a y value of 0, and this height is 0, and this height is 0. So that's a little bit more of like a conceptual question. And today we're going to solve polynomials where the height is 0, aka where are the x-intercepts going to be. And we're going to solve for the x-coordinate algebraically. So before we get into that, we got to do the zero product property. We got to get an idea of what the heck the zero product property is. And if we can answer these 3 questions, I think you're going to understand what the zero product property is. So first things first is, what is 3 times 0 going to be? Well, that's equal to 0. And if I asked you, well, hey, what is 0 times 45 going to be? You're going to say it's 0. Why would you say that? Because anything times 0 equals 0. And I mean anything. I mean 365 times 0, that's going to equal 0. I mean the irrational number pi times 0, well, you bet that's going to be equal to 0. Heck, even the number 1 times 0 is equal to 0. Heck, even the letter x times 0, that's going to be equal to 0. Anything and everything times 0 is always going to be equal to 0, and that essentially is what the zero product property says. So in words, the zero product property says that if the product of 2 expressions is equal to 0, then each expression is equal to 0 if they're unknown. So product in math life is whenever we multiply. So if we have 2 expressions that are being multiplied together and they're equal to 0, then that's saying either one thing that's being multiplied is equal to 0 or the other thing is equal to 0. And some examples, like the ones I'm about to show you here, it's obvious. It makes sense. You can tell which one is not 0 and which one is. But other times, when we're working through algebra problems, it is not obvious which one. So we're going to have to set both of them equal to 0. So in my first two examples, I have 5 times x is equal to 0. When I have two things that are being multiplied times one another and it's equal to 0, the zero product property says one of them is going to be equal to 0. Now, we can tell that 5 obviously not equal to 0, so x must equal 0. But we can also use some algebra skills to actually solve this and show you for sure that it actually is true, that x is the one that's equal to 0. Now remember, I got a product, 5 times x. So if I want to undo and get x alone, I have to use the inverse of multiplication, or the opposite, which is going to be division. If I multiplied by 5, I can divide by 5. Whatever I do on the left side, I got to do on the right. Now remember, it is okay to have 0 on top. 0 divided by 5 is just 0. So, we got 0 is equal to x. Perfect. Exactly what we said it was going to be. Same thing for the expression on the right. I have something x times 12 is equal to 0. Clearly, the unknown something, the x, is going to have to be the one that's equal to 0, but I can use division of 12 to simplify and get x alone. Again, remember, it is okay to have 0 on top, and you get x is equal to 0. Like I was saying, x has to represent 0 in these. Here, it was clear that we could tell which one was unknown, but sometimes it's not so clear which one. And so the zero product property tells us if a product is equal to 0, set each piece equal to 0. So here's our first example. X squared minus 3x minus 10 equal to 0. And you might be thinking, wait a dang minute. That last example was already in multiplied form. This is not multiplied form, which is where the haunting of the factoring comes back and bites you. Remember, we can rewrite polynomials in factored form. It breaks it up into smaller pieces, it breaks it up into multiplication, and they're equivalent. So, when we have a problem like this, what we're really asking ourselves is, where is this degree 2 polynomial? And it's positive, so we know it's going to look like this. Where is that crossing the x-axis? And so we're going to solve with algebra for this spot and this spot. But in order to do that, we need to rewrite that polynomial in factored form, use the zero product property to set each factor equal to 0, and then make sure we are making some sense here. So, to start us off, first things first is we need to factor this. Look at the very first term here. This says 1 times x squared minus 3x minus 10. Very first strategy we're going to need to use is, you could use the x box, but really just the x is all we need. We're going to ask ourselves what multiplies to 10, this last term right here, but adds up to negative 3, this middle term right here. So what two numbers multiply to negative 10, but add up to negative 3? And you're going to say, girl, that's 5 and 2. And I would say, you are so correct, but one of them needs to be negative. And it's going to be 5. Looking at our very first term, we have x squared. That can be written as x times x. So when I go to put all of this information into factored form, two things that are multiplied together, that is equivalent to x squared minus 3x minus 10, you'll see that the x goes in the first spot, and the negative 5 and positive 2 goes in the second spot. So we rewrote this polynomial in factored form, and now I have something times something is equal to 0. Specifically, x minus 5 times x plus 2 is equal to 0. So we're going to use the zero product property and set each factor equal to 0, because we don't know which one is the unknown 0. So we're just going to set them both. It's like reverse psychologying the own problem. So we're going to set x minus 5, this factor, equal to 0, and x plus 2 equal to 0. Using a little bit of algebra magic, we can solve and get x alone, and get x is equal to positive 5, and x is equal to negative 2. You with me? Again, remember the whole goal of this problem was to figure out when this polynomial, which we know looks like this, it's even positive, is crossing the x-axis right here, right? And so we just found out that one of these spots right here is at 5, and this other spot right over here is at -2. So one way to check that we did this correct is to count how many zeros we solved for. If we look at our problem, we got 2 zeros that we solved for. We got x is 5 and x is -2. This should always match the degree. Looking back at the original problem, the degree was 2, and also in factored form, there was 2 x's. If the zeros is the same number as the degree, we are in business. Let's do another, but let's make it a degree 4. How can we solve x to the 4th minus 3x squared minus 10 is equal to 0? This is very similar to the last problem. As a matter of fact, it's so similar that the only thing that's different is now we've got to the 4th power and to the 2nd power, versus the original problem was to the 2nd power and to the 1st. So we're going to use the same strategies. Whenever you have a degree 4, pretend it's a degree 2. The only thing that changes is that instead of x times x times x isn't x to the 4th, but x squared times x squared is. So again, we're going to ask ourselves what multiplies to -10 but adds up to -3. And we're in the same spot. It's -5 and 2, and so we fill in the pieces into our factor pairs, and we have officially rewritten this problem in factored form, which is multiplication. And now we can use the zero product property because I have x squared minus 5 times x squared plus 2 is equal to 0. So to use the zero product property, you need to set each factor equal to 0. X squared minus 5 needs to be set equal to 0, and x squared plus 2 needs to be set equal to 0. From here, we can solve with a little bit of algebra to figure out where my x-intercepts are going to be. However, when you have a degree 4, you end up in a slightly different place than we were last time. So when I set each factor equal to 0, I end up with x squared equals 5 and x squared equals -2. If I want to get x alone for the x-intercepts, I need to take the square root of both sides. So my first x-intercept is going to be at plus square root 5, but also minus square root 5. Whenever I have a square root, I could have the positive and the negative side. When I solve x squared equals -2, now I run into a unique problem. Whenever I have a negative in the square root, that means I have an imaginary solution. So this becomes plus or minus I square root of 2. Do you really think imaginary numbers were going to go far away? Come on now. How many zeros did we just solve for? Well, we've got 2 right here and 2 right here, so that's 4 total. What was the degree? Oh, yeah, the degree was 4, and there's 2 4x's in the factored form. So what does this end up looking like? Well, since 2 of my solutions have imaginary, what this is going to look like is something like this. I know it's an even degree polynomial and it's positive, and I'm looking for the x-intercepts. So one of them is going to be over here at the square root of 5 and the negative square root of 5, but these two up here, these ones that are kind of floating above, those are my imaginary solutions up there, which is kind of cool. We know that that's allowed to happen. Okay, let's do another problem. 2x to the 3rd minus 6x squared minus 20 is equal to x. Again, we need to rewrite this in factored form, then use the zero product property and set every factor equal to 0 to find all of the x-intercepts. One thing that we need to make sure every single time, and what we should be asking ourselves when we go to factor is there a greatest common factor? Is there something in common of all of the pieces? And if we're looking around here, we can see that all of these are even numbers, so I can divide by 2. But also, they all have x as a part of them. So if I factor out 2x, I then have x to the second power minus 3x minus 10 is equal to 0. And I'm right back at the same type of problem we were just at, man. I need to figure out what multiplies to negative 10 inside these sets of parentheses, but adds up to negative 3. And that's like the same type of problem. Now that I have the GCF, though, now I have 3 factors that I have to use the zero product property and set them equal to 0. So the first factor is 2x. Set that equal to 0. The second factor is x minus 5. Set that equal to 0. And the third factor is x plus 2. Set that equal to 0. Using a little algebra, your goal is to get x alone, and we will get x is equal to 0 as one of my x-intercepts. X is equal to 5 as one of my x-intercepts. And x is equal to negative 2 as one of my x-intercepts. How many x-intercepts did I just find? How many zeros did I just solve for? I solved for 3 of them. What was the degree of my polynomial? What was 3? And in factored form, there was 3 x's, so I know I found them all. And if I'm thinking about this, this is an odd degree polynomial, right? It's odd because the exponent is odd, but it's positive. Odd positive means that my graph is going to end positively, so it looks something like this. And what I just solved for was my 3 x-intercepts. One of them on the left, right over here, that's at negative 2. This one in the middle is at 0, and this x-intercept is at positive 5. That's crazy. Here's another one to solve. X squared minus 6x minus 16 is equal to 0. There's no GCF here. We're just going to ask ourselves what multiplies to negative 16 but adds to positive 6. That, of course, is going to be negative 8 and 2, and since the first term is x squared, that's x times x. Again, rewrite the polynomial in factored form. Check. Then use the zero product property by setting each factor equal to 0. X minus 8 is a factor, set that equal to 0. X plus 2 is a factor, set that equal to 0. With a little bit of algebra, we can find our x-intercepts. X is equal to 8, and x is equal to negative 2. I just found 2 zeros and 2 x-intercepts. I look at my problem, and I realize that the degree was also 2, so I know I found them all. This polynomial is even positive, so I know my graph's going to look like this. The x-intercepts are here at negative 2 and here at positive 8. So by solving and using factoring and the zero product property, I can actually get a really good idea of what my sketch of my polynomial looks like, which is what we've actually been doing the last couple of days. Whenever it feels like factoring is a little too easy, it's probably because the next example is going to use the similar idea. And that's exactly what this is. This is x to the fourth minus 6x squared minus 16 is equal to 0. The only difference between this problem is now this guy is x to the fourth, which is x squared times x squared. But we're still going to ask ourselves what multiplies to the last term, negative 16, but adds up to negative 6. And that, my friends, is going to be 8 times 2, where 8 is negative. We go to factor this, and now, since it's a degree 4 polynomial, we see that our factor pairs are x squared minus 8 and x squared plus 2. Set each factor equal to 0, since I rewrote the same polynomial in factored form, so now I can use the zero product property. X squared minus 8 equals 0, and x squared plus 2 is equal to 0. Excuse me. Use a little bit of math, and we will find that x squared is equal to 8, and x squared is equal to negative 2. Now, with degree 4 polynomials, you usually end up here. You usually end up in this situation where in order to get x alone, you need to undo to the second power, which is by taking a square root of both sides. Okay? But sometimes you need to simplify that square root. The square root of 8 becomes, 2 square root 2. And so I just found x is equal to plus or minus 2 square root 2 on the left. And whenever I have it equal to a negative, that's going to be the imaginary number I, and then whatever's left in the radical. So I just found 4 zeros plus 2 square root of 2 and minus square root 2 over 2. Also, plus I radical 2 and minus I radical 2. I look back at my problem. My degree was 4. I had 4 x's in factored form, so I found them all. What's crazy is 2 of them were imaginary and 2 of them were real numbers. When I go to graph x to the 4th, I know that that's an even degree and it's positive, so it's going to look like some sort of W shape. But when I do this, I only end up finding 1 or 2 x-intercepts, right? Maybe one's right here and maybe one's right here. That's maybe negative 2 square root 2 and the other one is positive 2 square root 2. The other imaginary ones do not touch the x-axis. They're floating above. And that's what we're finding when we are solving these types of problems. Pretty crazy, right? All right, 2x to the 4th minus 5x squared minus 12 is equal to 0. This is an Xbox strategy alert. The reason we have to use Xbox is because there's a number in front of x to the 4th. So we're going to start off by drawing our box and put the first term in the first spot, the last term in the last spot. And since those are the first two things we're putting in the x or in the box, we're going to multiply those two numbers and put them at the top of the x. So 2 times negative 12 is negative 24. So I want to know what multiplies to negative 24 but adds up to negative 5. And that is going to be negative 3 and negative 8. What's different about this is now I'm going to put negative 3 in, or positive 3 inside the box and negative 8 inside the box, but because it's x to the second power and the middle term is x squared, I had to make sure this was 3x squared and negative 8x squared. Once we're here, we're going to start to factor out the greatest common factor from each row and each column. So 2x to the 4th and negative 8x squared, that has a GCF of 2x squared. 3x squared and negative 12, that has a GCF of 3. 2x to the 4th and negative 3x squared, that has a GCF of x squared. I'm going to write it over here. And negative 8x squared and negative 12 has a greatest common factor of negative 4. Double check that when you multiply, you get the same thing. 2x squared times x squared does give me 2x to the 4th. 3 times x squared does give me 3x squared. 2x squared times negative 4, that does give me negative 8. X squared, 3 times negative 4, that does give me negative 12. So once I've used the x in the box, I can just put them in the factors. 2x squared plus 3 and x squared minus 4. Once I have it written in factored form, now I can use zero product property. Set 2x squared plus 3 equal to 0 and x squared minus 4 equal to 0 and solve my life away. Here I'm going to get 2x squared equals negative 3. Divide both sides by 2, I get x squared equals negative 3 over 2. And when I go to get this alone, this becomes a little complicated. The negative becomes plus or minus I, but I'm just going to leave it as square root of 3 over 2. Technically, we would do something else, but I'm not going to bring it up right now. I got 2 roots. For the next problem, I'm going to add 4 to both sides to solve this guy. That gives me x squared equals 4. I need to get x alone, so I'm going to take the square root, and luckily, phew, sometimes it works out to be a whole number, and I get plus or minus 2. I found 2 roots here, the plus value and the minus value, 2 roots here, the plus value and the minus value. So I found 4 zeros or 4 x-intercepts, and this is degree 4. 2 of them are imaginary, meaning they're floating above the x-axis. 2 of them are real numbers, meaning they're hitting the x-axis. All right, and one more strategy that we might need to use when factoring could be factor by grouping. The reason I know I'm going to have to use factor by grouping is because there are 4 pieces to this problem. 8x to the third minus x squared plus 56x minus 7 is equal to 0. Again, whenever we have an equation equal to 0, I want to know what are the x-intercepts. And one way to do that is to factor by grouping. Factor by grouping, so you need to split it in half and factor the greatest common factor on the left-hand side and the greatest common factor on the right. Both of the things on 8x to the third and x squared have x squared in common. And when I factor out that greatest common factor, I'm left with 8x minus 1. If I look at the right-hand side and see what 56x and 7 have in common, they have 7 in common. So I'm going to factor out a positive 7. And what's left behind, 56 divided by 7 is 8 with the x minus 1. And now I know I factor by grouping correctly if the thing in the parentheses matches. And would you look at that? The things in the parentheses absolutely do match. So I'm going to rewrite this as x squared plus 7. Whatever's outside the parentheses goes in their own. And 8x minus 1 as its own factor. So I have x squared plus 7 times 8x minus 1 is equal to 0. I rewrote the original problem in factored form, which is the same thing. It's just instead of writing it in addition subtraction, I'm writing it in multiplication. This is important because I need to use the zero product property. Since I have 2 or more things that are being multiplied and it's equal to 0, I want to figure out which one is going to equal to 0 by setting both of them. Set x squared plus 7 equal to 0. Set 8x minus 1 equal to 0 and solve. Sometimes we have a little bit of unlucky situations where we end up with an imaginary solution. I know I will end up with an imaginary solution whenever I have something to the second power equal to a negative. Remember that the negative can just be brought out as I, and if your value cannot be broken down anymore inside the radical, like 7, it can't be broken down, you'll just leave it inside the radical. However, sometimes we end up with this really cool situation with our factor 8x minus 1. This is a little different and not as hard as it seems. Add 1 to both sides, we get 8x is equal to 1. The last step here would be to divide both sides by 8, and here's a crazy solution. X is equal to 1/8. That seems really crazy, but it's true. Sometimes the factors are imaginary, sometimes they're square root values, sometimes they're just fractions, man. How many zeros did we solve for? Well, there's 2 over here, plus and minus, and a third one right here. What was the degree of this polynomial again? Oh yeah, it was x to the third. I found all of them. And for this polynomial, I know it's odd positive. And so one of these x-intercepts is at 1/8 and the other 2 are imaginary, meaning this is the only part that's touching the x-axis. Now that we have recapped factoring and this, you should be able, with factoring practice, be able to solve similar problems on your homework. Don't worry, there's more solving by factoring to come because we didn't cover all 6 strategies. However, there will be a lot to do in one little video. Have a good day.